Welcome to the first lecture of the McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. My name is Bill Farmer. We're going to start with the first topic of the course, Basic Mathematical Concepts. Many, if not most of these concepts, you should be familiar with from your undergraduate mathematics courses. Here's an outline of this topic. First, we're going to discuss a bit what is mathematics. Then we're going to look at mathematical proofs, what their purposes are, different styles of proofs, and techniques for producing proofs. Then we'll go on to a survey of different kinds of mathematical values. These will include numbers, sets, sequences, relations, and functions. And finally, we will survey mathematical structures, and we'll focus in particular on orders, algebraic structures, lattices, graphs, and trees. So the first question we want to deal with is, what is mathematics? Now, many people may think of mathematics as a gigantic body of facts. These facts include things like 1 plus 1 equals 2, the derivative of the exponential function is itself, the set of real numbers is uncountable, and so forth. But mathematics is actually a process for understanding the world, and in particular for understanding the mathematical aspects of the world. And these aspects can involve things like time, space, measure, pattern, and logical consequence, as well as other things. So mathematics is a process, and this process is based on mathematical models. And a mathematical model consists of objects, concepts about the objects, and facts about the objects and concepts. So the process works as follows. A model is created to describe a particular mathematical phenomenon that we see in the world. So for instance, we could create a model to capture the phenomenon of counting. And in this model, we could have objects as objects. We could have the set of the natural numbers. We could have concepts like the successor of a natural number. So the successor of 3 is 4. And we can use this to investigate how counting is done. Then the second important part of the process is exploring the model. By exploring the model, we can learn more about the phenomenon in the real world. By exploring this model about counting, we can learn more about counting. And we can do this by developing new objects, new concepts, and facts. So for instance, our model of counting, we could introduce the notion of addition. And the result is we get a richer model, a model with more objects and concepts and facts, and gives us a deeper understanding of the phenomena in the real world we're trying to understand. So that's a very quick overview of what mathematics is. It's important to realize it is a process. It's a process for discovering mathematical aspects of the world. Now, mathematical models can be explored in a whole variety of ways. And these ways fall into 5 groups: inference, computation, concretization, narration, and organization. Now, we don't have time to go into a lot of details of these, but I'll give some examples. So inference involves inferring new knowledge from knowledge we already know. And a good example would be proving a conjecture. We think something is true in our model, so we try to prove it. If we prove it, then we know that this thing is true in our model. There's computation. An example would be we have a mathematical expression that says something, and we simplify it using computation, and now we get an expression that's easier to understand, perhaps. Concretization refers to making things concrete. So we could have some phenomenon we're trying to understand, and we look at various examples of it. Collecting these examples is concretizing the problem. Now, narration is telling a story using natural language, telling the story in a linear way. Like, suppose we have these objects. We could define these concepts. We can state this conjecture, then we can prove it. You see this narration in practically every mathematics textbook. And finally, there's organization. We explore models using organization by identifying common structure, not only in the model, but in collections of models. Now these are the 5 aspects of what we call the Tetrapod Model of mathematical knowledge. So a tetrapod is basically the skeleton of a tetrahedron. It has 4 vertices and then it has a center. The first 4 aspects, inference, computation, concretization, and narration, they're at the 4 vertices, and the center has organization. So that's a quick overview of the tetrapod model, and this is a model that includes, among other things, the different ways we can explore mathematical models. So let's talk about what value structures and models are. So a mathematical model, and from now on we'll just a mathematical value, and from now on we'll just call that a value, is any object, concrete or abstract, that is used in mathematics. So any object that we're going to use in mathematics to do mathematics or talk about mathematics or study mathematics, we're going to call a value. A mathematical structure is a set of values that have been structured in some way. So a set of values with some kind of structure. So if you think of the set of natural numbers, these are the natural numbers of values. They are structured as a total ordering, where 0 comes first, then 1 comes, then 2 and 3, and so forth. Mathematical structures are usually gain their structure using a set of distinguished elements, functions, and relations. So we'll talk more about this as the course goes on. And values are the building blocks of mathematical structures. Using values, we build mathematical structures. Now, a mathematical model is a collection of objects, concepts, and facts that describes a particular mathematical phenomenon exhibited in the world. We've already mentioned this. We're not going to spend a lot of time going into many different kinds of mathematical models. Instead, we're going to be focusing on the building blocks of mathematical models. These are mathematical structures. Now, in mathematics, a proof is a deductive argument that shows that a conclusion follows from a set of premises. So suppose we have a set of things we believe are true or we want to assume are true. We call these the premises. And then using deductive reasoning, we come to a conclusion that something must follow from these premises. If these premises are true, something else must be true. And this deductive argument is a proof. And a theorem is a statement for which there is a proof. If we have a proof that a conclusion follows from a set of premises, we call that statement a theorem. Now, I mentioned that in the mathematical process, one of the key things we do is we explore models. And I mentioned there's lots of ways to do this, but by far the most powerful and effective way is using proof, using mathematical proof to explore mathematical models. And the approach is pretty simple. We have a model, we think something might be true about that model, we express that as a conjecture, then we try to prove the conjecture. And often when we're trying to prove the conjecture, we find out the conjecture is false, but the proof helps us modify the conjecture, and then we try to prove it again, and in time we end up with a conjecture that is true and a proof that shows that it is true. So proof is the central component of the mathematics process. And it is what separates mathematics from pretty much every other endeavor. It is the power behind mathematics. Now, unfortunately, many students of mathematics don't like proofs. They think they're hard. This is unfortunate because this is the power. The power of mathematics is proof. And in this course, we're going to spend lots of time reading, thinking, and doing proofs. Now, you might think that there's just basically one purpose of a proof. It is to show that we have a theorem, but actually there's many purposes of the proof. I've written down what I think are the really important ones, these 8. The first is by far the most important, communicating mathematical ideas. A proof shows why a theorem is true. It shows why a conclusion is connected to the premises, why the conclusion follows from the premises. So this is a communication purpose. This is the most important. The second most important purpose is certifying that a mathematical result is correct. If we have an if we have a conjecture and we want to know if that conjecture is true, the proof is a kind of certification. So these are the 2 most important purposes of proof. But proof is also used for organizing mathematical knowledge. We do this by building up a deductive edifice where we start off with some assumptions, and then using proof we derive a whole bunch of things that follow from these assumptions, and then we derive things that follow from the things that follow from the assumptions. So proof is useful for organizing mathematical knowledge. Proof is also very useful for discovering new mathematical facts. The way this happens is we state a conjecture, we try to prove it, we find out that the proof shows the conjecture is false, but the proof often indicates how we can fix the conjecture. So the proof helps us discover the correct conjecture, not the one we originally started with. Proofs are very useful for learning mathematics. The best way, by far, to learn mathematics is to read and write proofs. Proofs also are a way of showing the universality of mathematical results. So, you may have observed that 2 plus 4 equals 4 plus 2, or 6 plus 5 equals 5 plus 6. But if we want to show the universality of what's going on here, we would prove that addition, let's say addition of the natural numbers, is associative. So proof is a way of showing that results are universal, that they hold given certain conditions in every situation that satisfies those conditions. Now, another purpose of proof is to establish coherency. If we have a well-understood body of mathematical knowledge and we make a discovery, at least if we think we've made a discovery, we want to know if that thing we've discovered hangs together with our body of mathematical knowledge. Proofs are a way of showing that new results are coherent with old results. And finally, a very important purpose of proof is to create mathematical beauty. Now, mathematicians don't talk about mathematical beauty. They talk about elegance, but what they really mean is beauty. Many mathematicians are very motivated by beauty. They see their job as creating beauty, just like an artist may see their job as creating beauty. And some go so far as saying, I won't accept a theorem unless it has a beautiful proof. So these are 8 purposes of proof. And now let's talk a bit about styles of proof. How do we present proofs? There's many ways of doing this. I'm going to mention a few sort of common ways. One is, remember, a proof is going to be some kind of deduction. It's a deduction that shows a conclusion follows from a set of premises. One kind of proof is we just describe that deduction. Another kind is we prescribe how we produce a deduction. So we could say we start with the first 2 premises and we use a certain rule of inference to get a result. That would be the beginnings of a prescription. Many proofs are a mixture of description and prescription. A common kind of deduction is presented in a 2-column format. On the left side is a set of formulas and the right side is a set of explanations. And on the left side, these are formulas we believe are true, and on the right side, the explanations say how they follow from formulas higher up on the list. many proofs are presented as computations. We start with A, and from A we compute B, therefore we show A equals B. Another kind of proof that people are often very interested in are constructions. So we have a conjecture that says there exists a certain kind of object. So we construct it. We construct it from the things we know about. Of course, there are geometric proofs. The ancient Greeks were really one of the first people to really understand and value the power of proofs, but they did all their proofs geometrically. They didn't really have a sense of algebra then. And finally, there are visual proofs. These are proofs that convey lots of information just visually. In our discussion sessions, I'll give examples of all of these at some point. Now, there are two very important and competing styles of proof. We're going to talk about these in detail. The traditional proof style and the formal proof style. So the traditional proof style is a proof style that everyone normally uses. 99% of all people use this proof style. If you open up a math book, they're using this proof style. If you go to a math course and the instructor writes down a proof, they're going to use this proof style. So what is this proof style? The way it works is we present the argument of the deduction using natural language, but it's not exactly natural language. It's a stylized form. So we use special symbols, special notation, but it's basically rooted in natural language. So we're going to look at traditional proofs here. The natural language we're always going to use is English. And it's important to realize that these traditional proofs are geared for some intended audience. Now that audience could be a group of specialized mathematicians. It could be the students in a math course. It could be mechanical engineers. But it's important traditional proofs are intended for particular audiences. Now, traditional proofs, since they use natural language, they can be ambiguous. Natural language is ambiguous. So we don't know exactly, in some cases, what the proof is actually saying. Also, there can be assumptions that aren't stated. You know, in many proofs, there's many assumptions, and it's sort of a bother to have to state all of them, especially when you expect your audience to know exactly what these assumptions are. And finally, the argument could have gaps. We could just say we can derive B from A, but we don't say how you do that. Now, when someone writes a traditional proof, they're writing it for a particular audience, and they expect the reader to be able to resolve all the ambiguities, identify the unstated assumptions, and fill in the gaps. So this is how traditional proof works. And what's really good about traditional proof is the writer has great freedom, pretty much complete freedom to express a traditional proof in whatever manner he or she deems to be most effective. So the main focus is on the key ideas, making these key ideas understandable. And low-level details, like if we take two 4-digit numbers and multiply them together and get another number, we need that for the proof. Those kind of low-level details are usually either left to the reader to verify or they're done by computation. So in traditional proofs, writers try to express the key ideas as well as they can. They don't worry about things the reader can verify or things that can be done by computation and so forth. And traditional proofs are especially good for communication. The reason we have traditional proofs is they are the one way of doing proof that's really good for communication. But they're also good for human discovery. Remember I mentioned that you can use proofs when you're trying to prove a conjecture, especially a conjecture that's false. You can use the process of proof to discover conjectures that are true. And they're also very good for expressing beauty. So that's a traditional proof style, the style that 99%, maybe 99.9% of all mathematics practitioners use. So another form of proof, another style, is a formal proof. So a formal proof is a derivation in a proof system for a formal logic. So in a formal logic, we're going to have a language, and in the proof system, we're going to have rules of inference, and these rules of inference presumably are sound, which means if we start with two assumptions, A and B, and we use the rules of inference to conclude C, then we know C will be true if A and B are true. So a derivation is going to be a very formal thing. That's why it's called a formal proof. And these formal proofs can be presented by describing the actual derivation or by prescribing how it's created. Neither way is ideal. Now, what makes formal proofs really wonderful is that we can, because they're formal, they're manipulating formal expressions in a formal logic, we can develop software systems that help us develop formal proofs interactively. So someone sits down and they're going to write a formal proof, and the system can help them. The system can say things like, you can't use that rule of inference that way. You've misused it. And basically, we can build into these software systems the rules of the game in our formal logic. This is very useful, and even more useful, we can mechanically check. We can use the software to check our formal proofs. You can write a formal proof, and then the system will check and say, yes, this is really a formal proof. It's really a formal proof in the proof system for our logic. Therefore, we know that if our premises are true, the thing we proved is true. So this is very, very useful. It's particularly useful in the development of software because we can use formal proof to show that software has the properties we desire. Now, it's not all grand here. The writer is highly constrained. The writer is constrained by the logic. The writer has to follow the logic. By the proof system. The writer can only use rules of inference that are in the proof system. And every detail must be verified. So it is, even though the software is going to help us, producing formal proofs are very burdensome. And often the meaning of the theorem and the key idea of the proof may not be readily apparent to the reader. They get lost. Formal proofs are very good for certification. They're not so good for communication. They're also good for machine discovery because our proof is formal. That means we can write software to analyze it and discover new things. So formal proofs have their weaknesses, but we must say as strongly as we can that they provide a very high assurance that the theorem is correct. If we have a formal proof, it's not an absolute, doesn't provide absolute assurance that the theorem is correct, but it's very high assurance because we can check to make sure our software system is working properly. In fact, to write a software system that checks whether a proof is correct in a formal proof system is relatively easy. So we can have very high assurance that the theorem is correct. So this is why we have formal proofs. Now I'm going to end by quickly reviewing some basic proof techniques. These are techniques every one of you needs to know and be able to use. So I'm going to show the most obvious ways to prove different kinds of formulas based on the form of the formula. The first kind is implication. A implies B. The standard way of proving this is I assume A and then I prove B using A. The next kind of formula is the negation of A. The one standard way of proving this is I assume A, which is the negation of A. I assume A and then I try to derive a contradiction. I try to prove something that can't be true. If I'm trying to prove a conjunction, I first, let's say conjunction A and B, I first prove A, and then I prove B assuming A. The idea is I prove A. Once I prove A, I know A is true, so I can use that fact, and then I prove B assuming A. And usually you do it in this order. Usually you prove A first, and then you work on B. The reason you do it in this order is usually when people write down conjunctions, they write them down in this order because they're expecting someone is going to be thinking or trying to prove A first. Now a disjunction, A or B, there's two approaches. One is I can assume the negation of A and try to prove B, or I can assume the negation of B and then try to prove A. If I have a biconditional, which is sometimes called a logical equivalence or a bi-implication, A if and only if B, that means A and B are logically equivalent. The standard way of proving that is I prove A implies B, and then I prove B implies A. If I'm trying to prove an equivalence between two sets, S and T, then I prove S is a subset of T, and T is a subset of S. So that's the first set of proof techniques. The second set deals with universal and existential quantifiers, or universal and existential statements. So let's say I was trying to prove the universal statement for all members X in a set S, the formula A holds. The most obvious way to prove this is I choose an X from S that's arbitrary. So I don't assume anything about X. Usually all we have is a symbol. All we know about X is it's a member of S. Then we try to prove A, because A will be a statement about X. And if we can prove that, then we know the universal statement is true because we didn't assume anything about about X, except that X is in S. Another approach that's sometimes useful is we assume X is in S, and we also assume the negation of A, then we try to derive a contradiction. So this means that if we have a member of S, and it's not possible for A to be false, because if we assume A is false, then we can derive a contradiction. Now in some cases S might be finite, and in that case what we can do is what we have here. We can instantiate A with each of the members of S. So we get a finite number of statements, and we prove each of these individually. This obviously doesn't work, though, if S is infinite, like if S is a set of natural numbers. And fourth, which is a very powerful mechanism, or method, I should say, if S has a structure that admits proof by induction, then we can prove for all X in S, A holds by induction. So when we have the option to do proof by induction, this is usually our best choice. And now suppose we want to prove an existential statement. There exists an X in S such that A holds. The obvious way of doing this is we exhibit, we find, we construct some member A in S, then we instantiate the formula A with this member, I should say the formula capital A with this member little a, and then we prove it. So basically what we're doing is we're proving that A holds for a particular member of S. So that's the standard way of proving existential statement. We could also take the negation of the existential statement, which will be this universal statement that I have down here. The statement that for all X in S, the negation of A holds. And then from that we'll derive a contradiction. Okay, this concludes our first lecture on this topic of basic mathematical concepts. Thank you.